Did you guys get page 1 done yet? Brian, what's my limit for number 1?
Number 1 at -1.
Oh, I'm sorry, at the top. So we're supposed to consider the limit as x goes to 3 for each graph, period, not question mark. So what's the limit as x goes to 3 for this graph? This one?
Yeah. Or wait, no, sorry, it's 5.
Yeah, this one's 5. Yeah, limit as x goes to 3 is 5. Oops, is 5. Okay, and the next one is does not exist. Why does it not exist on the next one?
So if you go to 3 from the left, the limit is not the same as you go to 3 from the right.
Right, that's right. What specifically is the limit on the left?
5.
Right, this side's 5. The other side is 2, right. So your limit means what are you approaching? So on the left we're approaching y equals 5, on the right we're approaching y equals 2. And so we would say that the limit does not exist. This is one type of D&E. The next one is, so what's the limit on the next one there? 4. Yeah. And the arrowheads mean nothing, right? You're supposed to be focusing in on x equals 3 without actually looking at x equals 3. So you're looking at the curves near 3, but not at 3. Okay, next is this one. Limit as x approaches 3 from the left is negative infinity, but the right side is what? Right. So this is another case of what? Does not exist. So really does not exist means does not agree. That's what it really means. Okay, yeah. Notation of limits. You guys know the plus, minus, what all that means, right? So not a big deal. I don't like the way this is written. I don't like how he said the notation means limit. It should say that the notation is pronounced the limit of f of x as x approaches c equals L. Or the limit is L, you could say. I don't think it means that. It just, that's how you say it. As x gets closer to some number but does not equal that number, the value of the function, that means the y values, gets closer and closer to some value. We have the left and right notation, the minus and the plus. Let's look at the next picture. Okay, so what did you put on this one, Danica? 2. 2.
X from 1 to the left is 2.
That's correct. How about 1 from the right?
2.
Yes. So how about 1 in general? 2, right. So when there's no superscript, it means both sides. So hopefully you've looked at left and right already. Next is 2 minus, 2 plus, and 2 in general. So what did you put for this one, Audrey?
1 from 2 minus 0 for 2 plus, and does not exist.
Right, so in red here, the graph is approaching 2 on both sides. The limit is 2. Even if this point is empty, the limit is 2. And on the other one, no, it's okay. So notice you're not actually supposed to study x equals 1 and x equals 2, but only the graphs on your right. So because these are kind of coming together, that limit is 2. And because these are not coming together, that limit does not exist. Do you think it's possible to get D and E if we do a one-sided limit? Like, do you ever think that the question here might be D and E, D and E, D and E? Does that ever happen? No. Because D and E means the two sides are different numbers. Or one's infinity, one's infinity. So you can't have D and E for a one-sided limit. That makes no sense. There's another kind of D and E you guys know about, and that's where a graph, let me add a little bit to this little picture. Let's say that this goes like this, and it starts to look like cosine or something. Wiggling up and down forever. It's also true that LIM, x goes to infinity, here is D and E. but it's for a different reason. What do we mean by D and E in this situation? Brian, what does it mean?
There is no approaching y value.
Yeah, the graph doesn't approach any particular y value. That's right. So D and E can have multiple meanings. There's another kind of D and E. It's kind of a weird one, but if you look at sine of 1 over x as x goes to 0, this is a weird one. This is really hard to understand. But if you understand that this is the same question as this one, and this one, it's actually both of these in one. These two mean the same thing as this, because this means both sides of 0. And so if we do a negative and positive infinity and flip this over, if we study both of these reds, it's the same thing as studying this one blue limit. And both of these are D and E, so that's D and E. So this one's a really strange one. But that one's also D and E. Yeah, question?
If they give you like a limit as x approaches 0 from the right or the left, then that would equal the limit as x approaches infinity from like the left or the right.
Negative, positive, or negative. Yeah, that's right. So let's review that real quick. That's an important idea. We've seen several chances to use it this year. If you ever see this problem and it just looks too hard to solve, feel free to switch it to this problem because it's exactly the same question. It's exactly the same problem. Or if you see LIM, x goes to 0 plus, and you just don't think you can handle it, look at it from this perspective. Flip all your x's upside down. Oh, by the way, if you see any one of our x's, flip them upside down too. But it allows you to switch it to a different style. And if you have the Barron's book, the Barron's textbook has a whole bunch of these, which is cool because they're really good practice problems. Danica, you have that book, right?
Yeah, I just ordered it so to come today.
Yeah, you'll see, if you look at the limits section, there's a lot of problems that are LIM 0 minus and LIM 0 plus. And you can switch to these. Or if you see a negative infinity problem that bothers you, switch back to that. See? So this brings up a question. What if you're given an LIM x goes to 0 problem and there is no superscript? So let's say you're given a problem like this, and you just don't think you can handle that limit. You just don't get it. You've tried L'Hopital's rule. You're having a lot of trouble with it. Which side of 0 is this asking about? Both sides. So you have to split this into two problems, don't you? One where you're going to negative infinity, and one where you're going to positive infinity, and you have to check for agreement. The final question will be, do they agree? So I had fun with the Barron's textbook. I found a couple problems like this where I split it into two problems. Try them both and see if they agree. But they make for an interesting set of problems. Okay? So after you do those ones in your book, Danica, you can share your knowledge with others, and I'm sure you'll learn it really well then. Okay, let's go to the next page. What does continuous mean? So continuous means you don't have to lift your pen. That's really what it means. You don't have to lift your pen. So let me ask you, if I graph this graph, this is the point CF of C, why is it that I didn't have to lift my pen when I drew this graph through C? Why did I not have to lift my pen? It's continuous. Okay. Why is it continuous? Don't say because I didn't have to lift my pen.
All points in the curve exist.
They all exist. Well, that's true, though, for this red graph, too, isn't it? All points exist.
Number at C and the limit exists.
Okay. Yeah, so the reason that I didn't have to lift my pen is because when I was drawing on the left here, when I was coming from the left side, let's follow in blue. When I was coming from the left side, my y value was approaching f of c. when I actually got to C, my y value was f of c. And as I was leaving C, my y value was f of c. In other words, I never had to lift my pin because the approaching value, the at value, and the leaving value were all f of c. So this is why mathematicians say that the definition of continuity is that the left limit and the right limit and the value at the point are all equal. They are all f of c. So they write it as a three-part statement. I write it as a three-way equality. Okay? But let's take a look at example there. Is it continuous at x equals 2? Well, let's check the limit on the left. We'll check the limit on the right, and we'll check f of c.
Did you mean to write the limit as x approaches c from the left?
C, not zeros. Thank you. Yes, I meant to put a 0, a C minus, and a C plus here. C could be 0, but it doesn't have to be. Right, thank you. Okay, so this is exactly how you want to check for continuity. And you want to show this work, because if you do not write this on your AP exam, they will not give you full credit. You have to actually write LIMs for this sort of thing. No, you can have those in either order, as long as you have both. So you actually have to kind of write this on the AP exam. C is 2 in this problem. You can see the only place the graph might have a break is at x equals 2, see? So you want to show your work like this. Does this equal this? That's the first question. Then on the next line, go ahead and evaluate the limits. Now, 2 minus means 2 from the what? Left. So you'll be plugging 2 into one of these expressions. Which one? The top one, right? So what I would do is write this. LIMC goes to 2, and you can drop the superscript now. You don't need it anymore because you're going to write x squared plus 3 here. And then on the other side, you're going to write LIMC goes to 2. This time you're doing the right piece. So what would you write here? Yes, after writing this, go ahead and plug in the 2's. Is 2 squared plus 3 equal to 3 times 2 plus 2? And the answer is no. Not equal. Okay? Yes?
The second step where you drop the superscript, do you have to write that also on the AP test? Or
Yeah, I think you should. I really do. Because when you justify continuity, you're supposed to do like a little 3-stage proof. Okay? You remember in geometry class that even if you don't write the givens, your proof is considered wrong. Yeah, proofs are a little more strict than your average problem. Your answer is the work shown. Yeah. Okay. Now these didn't come out the same, right? That's 7 and that's 8. So I don't feel any obligation to do the third part of the test where I show that these are both equal to f of c. I'm not going to do that. They didn't equal each other. Well, let's look at the next one. So now we have to choose an A and a B that force continuity and differentiability. By the way, what's the difference between continuity and differentiability? How would you define that difference, Audrey?
Differentiability implies continuity, but continuity does not imply differentiability.
Yeah, you're right about that. If a curve is continuous, that does not necessarily mean it's differentiable. Here's an example. This graph look familiar? This graph is perfectly continuous at 0, but it is not differentiable at 0, right? On the other hand, if you have a graph that is perfectly differentiable at 0, that implies it must have been continuous. So you're right, but what's the difference between continuity and differentiability?
And differentiability has a slope.
Yeah, you should be able to draw a tangent line. for one thing. And that tangent line should have a slope that we can understand. So if the point is a sharp turn, how are you going to draw a tangent line? You're going to draw this or this? What are you going to draw? You don't have a specific tangent line there, do you? If the graph looks like this, you have the same issue. It's hard to pick out what the slope is at that point. In fact, there is no specific one. Another case is sometimes the graph is just simply broken, like this. You shouldn't be drawing tangent lines here, should you? But there's a fourth kind where it feels like you're drawing a tangent line, and you are. Unfortunately, we can't quantify its slope. This is probably the most special case of non-differentiability, and that's the vertical tangent. The line is perfectly drawable, but it doesn't count. It's not a slope. Okay, so either the tangent line doesn't exist, or it exists but has no numerical slope. So it just basically means has slope. Now my pre-calc students, I told them that differentiable means has slope, and then when I gave them the test, they got it backwards, and they thought that differentiable meant that it had a sharp turn. So they really messed up their test. I let them do corrections. But you guys see, they thought that differentiable meant not smooth. Differentiable means smooth and with a slope. Okay, so let's talk about this problem for a minute. If we're talking about negative x squared, that's this parabola specifically. But we're interested in that parabola for all x is less than 1. So this is actually the left-hand side of the graph. Y equals negative x squared. The other part of the graph, I'll draw in blue, it's just ax plus b. What kind of shape is that? That's a line. What's the slope of ax plus b? We don't know. We don't know the slope, nor do we know the y-intercept. So is it this line? Right? Is it this line? Is it this line? Is it this line? Is it this line? We want it to be that last one. We want it to be this one. We want the slope to be exactly right, and we want it to be filled in, and we want it to look where, after attaching these together, we get not only continuity, but we want to have it perfectly smooth. If this was a roller coaster and a train, the roller coaster was going up over the track. As you pass by this point, you would notice, hey, we're not going on a curve anymore, but you wouldn't feel any jolting. You guys ever been on Ghost Rider at Knott's? That track definitely has some non-differentiable points, because I get a headache every time I go on that ride. But I never get that feeling at Magic Mountain. The curves on those tracks are perfectly connected, it seems. Not only connected, but also smooth. So we're going to have to design the slope and the y-intercept very carefully. So I'm sure you guys know how to do this problem. Set them equal to each other to make sure they connect. And we also want their slopes to equal. So set their derivatives equal also, right? Okay, but how you show your work is important. So here's the student who does it probably a little too quickly. I'll show you the student who does it too quickly and might not get full credit, and then I'll show you the student who does it so formally it takes forever. Okay, ready? Here's the student who does it really quickly. Negative x squared equals ax plus b, where x equals 1. Plug in 1. Negative 1 equals a plus b. Hang on to that. Derivatives. Negative 2x equals a, where x equals 1. Plug it in. Negative 2 equals a. So what I did was first I set the expressions equal. This is to force continuity to make sure that they actually connect, that their y's are equal. Since what x equals 1 was the breaking point between these curves, I plugged in x equals 1 and I got this statement, negative 1 equals a plus b. I did the same thing with their derivatives. Negative 2x, and the derivative of that is just a instead of equal. Again, x is 1, so negative 2 equals a. Now I can take this negative 2 and plug it in here. And I get negative 1 equals negative 2 plus b. B is 1. So a is negative 2, b is 1. This student got the right answer, but they didn't do any limit notation. Like there was no limits anywhere. At least on the continuity part, they were supposed to show limits, right? Now 9 times out of 10, maybe more, 99 out of 100 times, I've seen that this is a multiple choice question on the AP exam. So it wouldn't matter if I showed you work. As long as you get the right answer, it doesn't matter, right? But if you really want to show your work for this, this is how it needs to look. And since you guys are probably serious students and you want to kind of show your work formally, this is what you need to do. First you need to write LIM, x goes to 1 left of f of x needs to equal LIM, x goes to 1 right f of x. Dropping the superscripts, LIM, x goes to 1, negative x squared, equals LIM, x goes to 1, ax plus b. Plugging in the 1, negative 1 equals a plus b. Full credit. It's exactly the same conclusion we had 2 seconds ago. Alright? Stage 2. This is the tricky part. I'm going to erase the roller coaster and draw something else. This is a hard one. You have to show that the slope between this point and a point on the left, the slope has a limit equal to the slope between these two. Okay? So I'll show you what I mean. You're going to use definition of derivative. Let me label these points. This first point in the middle is C. Actually, is 1, I mean. This is the point 1 plus C. And this is the point 1 plus C. I'm sorry, 1 plus H. Sorry, guys. These are the points 1 plus H on either side. On the left side, it's H goes to 0 from the left. And on the right side, it's H goes to 0 from the right. So you actually write the definition of derivative twice. Once like this. LIM, H goes to 0 minus f of 1 plus H minus f of 1 over H. This means the derivative at 1 on the left side. And then you set this equal to LIM, H goes to 0 plus f of 1 plus H minus f of 1 all over H. You're going to be plugging in 1 plus H into the left piece. It's going to look like this. Negative 1 plus H squared minus negative 1 squared all over H. Then you can drop the superscript. And then on this side, plug in 1 plus H into the right piece. A times 1 plus H plus B minus A times 1 plus B all over H. And this will lead you down the long and arduous road where A is negative 2. Okay, so what did I do? I plugged in 1 plus H and 1. That's these 2 points into the difference quotient. So it's just basically rise over runs. F of 1 plus H minus f of 1 all over 1 plus H minus 1. So that's the slope between there and there. Slope between there and there is on the other side. Now if you simplify all this, guess what? You get A equals negative 2. So I'll show my work. A lot of work here. LIM, H goes to 0. We have negative 1 minus 2H minus H squared plus 1 all over H. And on the other side, limo, A plus AH minus plus b minus a minus b all over h, and stuff starts canceling out like crazy. On the left side, if you take out an h, you get negative 2 minus h. On the right side, if you take out an h, you just get a. And if you let h go to 0, you get negative 2 equals a, like I told you. But this is technically the formal work. You do a one-sided derivative, it's called, which is really the definition of derivative for c plus h minus c with 0 going from the left. And that's a lot of work. Fortunately, it's been all multiple choice for this question as far as I've ever seen, so you'll never have to show this work. You can just set the derivatives equal, set the functions equal, which would have probably been your first thought. So why don't we let students just do that when they're showing their work? It's because you really don't have any business plugging in x equals 1 here, because the first piece doesn't even allow x to be 1. So it's kind of iffy that you would do like f prime. You know, why are you doing the derivative at 1 if the function's broken at 1, or potentially broken at 1? So formal work for that. That's how you do it anyway. Let's move on though. Why don't you guys take a few minutes and look at pages 3 and 4. I'll pause this. Let's go over this page real quick. So what did you put for number 1 there, Brian? And number 2? And 3? Right. So being bottom heavy, top heavy, and of equal degree. We get these 3. Okay, and you guys know what it means. It means that this graph approaches 0. This graph approaches infinity. This graph approaches 2/3. Right? Okay, and then this next one, you're going to have to ignore some terms, right? So Danica, what did you put for this first one? 0. Right. You're going to have to look at these two, right? What did you put for the next one? Right. The top has 5 powers, the bottom only 2. The next one? Right. And the last one?
0.
Why 0?
Because e to the x grows faster than x to the 3.
Correct. Or we could use L'Hopital's rule. When you take the derivative the first time, the top is 3x squared plus 5. If you take the derivative the second time, you get 6x. If you take the derivative again, you get 6. If you do that with the bottom, you just get e to the x minus 100. The next time it's e to the x. The next time it's e to the x. So on the third derivative, it's still got an e to the x on the bottom. But the top's only 6. Good. So that goes to 0 eventually, or right away if you see it. Let's go to the next set. So how do you find a horizontal asymptote? Why is this being asked right in the middle of a limit as x goes to infinity problem? It's because of these two statements. So you can't separate the idea of limits to infinity from the idea of horizontal asymptotes. They're the same question, right? So how do you solve horizontal asymptote questions? You have to do 2 limits per problem, right? So some people got this wrong on the Tuesday review. So let's make sure you go over these. So what happens when x gets large? What do you think, Audrey? If you do LIM, x goes to infinity on this one, what are you going to get? Yeah, that's correct. So this term will dominate the numerator. It's the only term there. This term will dominate the bottom, so you'll get 1. What happens if you do LIM, x goes to negative infinity? Which term dominates the top? We don't have a choice. It has to be this one. But which term dominates the bottom now? What do you think, Brian? Which term is more dominating now? But x is going to negative infinity, right?
Oh, negative x squared.
The 2x squared is going to dominate. 3 to the negative a million, 3 to the negative a billion, 3 to the negative a trillion is going to actually be minuscule. So what we're dealing with is this situation. Be careful here. Even after reducing it to this, you have to ask yourself, which of these dominates? Be very careful. The bottom dominates. The top is very close to 0. Boy, you got to be careful with that one, don't you? So I had a professor who taught this a little differently, and I really liked his method. I didn't use it very often, but it's really helpful on this problem. Here's what my professor did in college. My professor would look at the entire fraction, and he would ask which term dominates all of them. I don't want to have 3x squared, I should say 3 to the x there. So he would say which function dominates out of all three. So choose one. You can only choose one. Is it 3 to the x, 2 to the x squared, or 3 to the x? So 3 to the x dominates for large values, right? So what he did was he would, for his positive LIM, he would divide everything by 3 to the x. So he would take take his numerator, divide it by 3 to the x, take his denominator terms, divide them by 3 to the x, divide everything by 3 to the x. And so he was left with this very simple problem. And since when x was large, this term would go to 0, he would get 1. Then he would do the same thing for the limit as x goes to negative infinity case. Only this time, who's the dominant term out of all three? Who's the dominant term when x is going to negative infinity? 2x squared, right? So he would divide this by 2x squared, divide this by 2x squared, divide this by 2x squared, and he would get this problem. And you told me it's the dominating term, so no matter what, these are going to both go to 0. So he would always divide by the most dominant of the functions, and then whatever's got that left in the bottom will vanish. That was kind of a cool way to show your work. But if you really think about this carefully, you should be okay. 2 years ago, they gave a problem like this on the AP test. The nation did so badly on this problem that they actually tossed the question out, which they shouldn't have. The question was perfectly fine, but they told the teachers, you're not teaching it right, go back, teach it again, which means they're planning on recycling that. So you'll see it on this year's test, I'm sure. Make sure to check both limits. We could do this one a lot faster. What are the answers on this one?
For the other one, would there be two asymptotes? One
Yeah, so what it means is your graph on the right side is approaching y equals 1, and your graph on the left side is approaching y equals 0, is what it means. And of course the graph could have two end behaviors, right? There's two ends. So what about this next one? Let's see if we can do this one in our head. So this one, the answer was y equals 1, y equals 0. What about this next one? Yes, y equals 1 and y equals a half. If you're going with positive large x's, you can see it'll be 3 to the x over 3 to the x. If you're going with negative x's, these guys don't matter, and you get 1/2. Good. So exponentials tend to vanish when x gets very small, or negative, very negative. How about this next one? If x is extremely large, you should be looking closely at these two terms. And forget the 2x squared, right? If x is a million, billion, trillion. So what does this go to? No. Zero. An exponential base 4 grows faster than exponential base 3. You could do L'Hopital's rule on this. After a few derivatives, you'll see that the top is like 3 to the x ln 3, and then ln 3. Every time you take a derivative, we get another ln 3. The bottom, the 2x squared will go away after a couple derivatives. But the bottom's just going to look like 4 to the x ln 4, ln 4, ln 4. So after like 3 or 4 derivatives, you'll see the 2x squared's gone. But this thing is still bottom heavy. How about, is this hard to believe? Do you guys have a hard time believing that this goes to 0? What if I wrote it like this? What if I wrote 3 to the x over 4 to the x as 3/4 to the x? You wouldn't have a hard time believing it goes to 0 now, right? What's 3/4 of 3/4 of 3/4 of 3/4 of 3/4? 0, right? See it better now? Okay. So when x is extremely large, y goes to 0. If x is extremely negative, your dominant term is right here. These others are small, so it goes to 0 again for a different reason. So this graph is an interesting one. It goes to 0 on both sides. I don't know if they're both above the axis, but they both go to 0, you see. All right, so be careful with those. Those are tough. Next page. Definition of derivative. There are 3 definitions of a derivative. I'm going to lecture this part. I've listed them in order of frequency and how it's tested. So I just want to draw a quick little picture for each of these. This one is if you pick the point x, f of x, and a point nearby at x plus h, comma, f of x plus h. What you're looking at here is the slope between these points. Okay, so if you want to draw the slope of this line, or this line here, and find the slope, you would do y2, right, minus y1 over x2 minus x1. But what's x plus h minus x? It's just h, right. So the picture that goes with this is this one. You've got 1 point at x, 1 point at x plus a hair, h. And so you then make the h shrink to 0, which brings the right point onto the left point and creates a tangent line instead of secant line. This is the most commonly tested one by far. Okay? There's another definition right below it here. It's tested about 1/3 as much. Okay? And that's this definition. And the picture's a little different. It looks like this. So you have x and a. So this is the point x f of x and a f of a. And the slope between them is f of x minus f of a over x minus a. And this time we're trying to get x to collapse onto a. So we're making x go to a. See? A little bit different. What ends up happening is you get f prime at a. So it's not quite the same thing. The first one gives us expressions. So this will yield derivative functions. It yields derivatives as functions. You know, like 2x squared plus 5. This one will give you numbers. It yields slopes at a. So same idea. The second one is often used if you want to find like the slope at 4 or something. A would be 4. Then this last one, don't let it intimidate you. This is actually the one your calculator uses, I believe, to calculate a derivative. And the picture looks like this. X is here, and there's 2 points on either side of it. This is x minus h, and this is x plus h. So this is the point x minus h, f of x minus h. That's this point. And this is the point x plus h, comma, f of x plus h. But again, it's just the slope between them. So the curve runs like this, maybe. But the red line straddles right over x. X is in the middle. So when you do the rise over run, you end up subtracting the y values. I'll write it in black. F of x plus h minus f of x minus h. And now the distance between these is technically 2h. And then you make h shrink to 0. And the 2 points collapse from the sides, one on each side. They all collapse toward the middle. But it gives us the slope of the red line as a tangent line, so to speak. All three do the exact same thing. The first and third ones yield derivatives as functions. The middle one yields derivatives as values. They really are tested in this order of frequency. So you probably will be very unlikely to see that last one, but know that the last one has a name, the symmetric difference quotient. Why symmetric? Because there's one on each side. The symmetric difference quotient. The other two are just called difference quotient. By the way, difference quotient is the name of the fraction. This is the difference quotient. Once you put the limit on there, it's called a derivative. Okay. All right, let's look now at how they test or how they ask questions. So you can kind of scroll down, or I'll scroll down, you kind of look down. Oh, let's see. Let f be a function defined in this way. Oh, this is just a repeat of what we've already done. So let's skip over this page. Let's go down to here. Let's go to this part, guys. This is a very important question. I think this was on the 2008 test. I forget which test it was. But look closely at it. Which of the three derivative formats does it match best? Yeah, it looks like f of x plus h minus f of x over h, LIM, h goes to 0, right? It does, it really does. What does it look like x's on this problem? I mean, you can see from direct inspection that this one says f of 3 plus h, and this one says f of x plus h. So what is my x in this problem? 3, yeah. This says f of x, this is f of 3. It looks like x is 3, you see. So x is 3. What does this whole thing mean? This is the definition of a derivative. So all of this, LIM, h goes to 0. This means f prime of 3 is what it means. The whole thing means f prime of 3. So this sentence is f prime at 3 is negative 2. Ah, that's very meaningful. Sounds like there's a slope at 3. It means the slope at 3 is negative 2. That's what it means. Okay, now we can answer the question. If this statement is saying the slope at negative 3 is 2, then is f continuous at 3? Yes, it is. They wouldn't be giving us a slope if it weren't continuous. The next bullet there should say differentiable. Sorry, that's a typo. This should say differentiable. Make that correction, sorry. Would you say that f is differentiable at 3? Yes, it is. It has a slope at 3. Is the derivative of f continuous at 3? That's going too far. So this one's Roman numeral 1 and 2. Now you might think, well, how can the derivative be discontinuous if the function is differentiable? There is a special case. I researched this topic for like an hour one day. There is a graph where the function is the derivative function looks broken at 3, but the original graph is smooth at 3. So, listen, you don't want to make statements about f prime. Okay, listen, this is really important. This is a tiny bit of information about f. It tells us a tiny bit about f. Just one slope at one point. How would we ever dare venture to talk about f prime graph? I don't even dare. Okay? So 1 and 2 only for that one. Well, let's go to this one. Let's just repeat again. It's a good one, but you can try it later. Let's look at the mixed practice here. And the answers to everything from here on out are on the back there. You guys should have grabbed page 9. That has all your answers. So go ahead and give them a try. Oh, are there?
Yeah. Oh, wait.
On the answer sheet or the?
My mixed practices is 1, 2, and 3, and then on the next page it says 3 again, and then 4.
Oh, flip that one over. You have duplicate pages?
Well, no, there's like 1 through 9, and then there's multiple choice. That's 1 through 11.
Yeah, there's 2 sets of problems. There's mixed practice, 1 through 9, correct?
Yeah.
Yeah, there's mixed practice 1 through 9, and then there's multiple choice 1 through 11. So your pages might be out of order there. Multiple choice, there's one multiple choice number 3 and one non-multiple choice number 3. Okay, you guys can work on these limit problems later if you want. The only one I wanted to kind of draw your attention to was number 6 and 7. So why don't we zoom in on 6 and 7 here. Everyone find these 2 problems? Okay. This one says limit as x goes to infinity sine x over e to the x. So what is the answer to this problem? What happens to this expression when x gets extremely large? Does sine x grow? Not really. Sine x doesn't really grow, right? So if sine x doesn't really grow, but e to the x does grow, what's this going to do? It's extremely bottom heavy, right? So this is going to go to what? 0. So what's weird about this problem is you don't feel like you can show work, you know? It's really frustrating. Even L'Hopital's rule is a joke. Watch this. Oh, I'm going to take the derivative top and bottom. Ready? Wait, I'm not allowed to. Why not? No. You're only allowed to use L'Hopital's rule when you have infinity over infinity. Right? So when x is large, sine x isn't large. And I'm allowed to use L'Hopital's rule. See the problem? You can't use L'Hopital's rule because the top isn't growing to infinity the way the bottom is. You're only supposed to use it in this infinity over infinity case or 0 over 0 case. So I'm not allowed to use L'Hopital's rule, and yet we know the answer is 0, but there's no way to show your work, and that can be really frustrating to some students. So let me show you how you show your work on this. It's called the sandwich theorem. We know that sine x over e to the x is certainly less than or equal to 1 over e to the x. Why? Yeah, sine x cannot exceed 1. Do you guys agree with the statement that I just wrote? And at the same time, sine x over e to the x is greater than or equal to negative 1 over e to the x. Do you guys agree with that statement? Since sine x is bound between negative 1 and 1, this extended inequality has to be true. Okay, now let's put in an LIM. X goes to infinity here, here, and here. Now the middle one was giving me trouble, but the ones on the ends aren't. They're easy. What happens to the left side of this triple inequality when x gets large? It goes to 0. This one in the middle is driving me crazy. I'm just going to leave it there. What's this one on the right going to go to? 0. Oh, so this one's getting sandwiched between 0 and 0. What does that tell you that it is? If something is between 0 and 0 inclusive, then its value is what? 0. Yes. This is how you can show your work. This is called the sandwich theorem. It seems like a really lame rule, but actually it's nice. It allowed us to show a little work on this one. And it allows us to believe it with our whole heart. Very cool. Now on the next one, should I do the same thing? Should I sandwich this between negative 1 over x and positive 1 over x? Not necessary. Just plug in pi over 4. Root 2 over 2 over pi over 4. 4 root 2 over 2 pi. So the reason I wanted to do 7 was I want to remind you that when you're finding a limit, sometimes it's as simple as plugging in the number, right? Don't forget about that. With all the cool tricks you know about limits, don't forget about the basics. Those are the only two I really wanted to go over.
For number 6, would you just say the answer is 0? Or would
The
you
answer is 0, and we've got proof, you know.
So you wouldn't have to say like the answer is 0 due to the sandwich theorem.
If someone asks you why is it 0, the best answer is the sandwich theorem. A lot of students don't know why it's 0. They just know that, well, the top is negative 1 to 1, and the bottom is like 80,000 trillion Google. So, of course it's 0. But this is much more convincing. You got something stuck between 0 and 0. I never really saw the value of the sandwich theorem until I tried to start showing work for all my limit problems. I realized I don't know how to show work for this one. Sandwich theorem built me out.
If it asks for like the limit as x approaches infinity sin x over x, isn't that just 1? So how would you show work for that?
If this had been sine x over x, and you're going LIM, x goes to infinity, the sandwich theorem would come to the rescue again. Yeah, you would sandwich it between negative 1 over x and positive 1 over x. And you do an LIM, x goes to infinity here, 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 and you get 0 is less than our limit, is less than 0. I think you're thinking of sine x over x as x goes to 0.
Okay.
That's 1. Okay, let's move on to the last page and then we'll call it a day. Just the multiple choice here. I wanted you to take a close look at these. Look at number 1 there. What does this look like? Look at the whole thing. Look at it holistically. This is the definition of a derivative. So this stands for d dx of something. Now remember, this part here is f of x plus h. And this part here is f of x. So what is the function we're differentiating? Evidently, we're taking the derivative of sine x. So what's the answer to this problem? Cosine x. It's clever how they ask these questions. It's really a derivative problem in disguise. Pretty sure the next one's a typo. This should say cosine here. But can you tell me what's going on in this problem? What are we taking the derivative of? Don't forget to change this. This should say cosine. I'm pretty sure it's a typo. Did you guys fix that? Okay, what's the function we're taking the derivative of? Cosine x. And what x value are we interested in plugging in? Pi over 3. But we would do that after taking the derivative, right? Okay, so first you would take the derivative of cosine. What does that give us? Negative sign. Then we would plug in pi over 3. So watch your order of operations there. You wouldn't plug in the number first. Then your derivative would always be 0. Right? First you take the derivative of this function. Then you plug in the f value, which is pi over 3. And then you're going to have to know your unit circles. So let me teach you a cool trick for unit circles. Hold up your hand. It doesn't matter right hand or left hand. You guys use your right hand in physics, right? So let's use the right hand. Brian, you might want to learn this trick. It's pretty cool. This represents, I'll turn my hand this way. This represents 0, 30, 45, 60, and 90. Okay? So let's say that you want to study 6 degrees. That's this way here. Pi over 3. Pull this finger down. Or actually this finger. Wait.
this side, well, how many fingers do you have on this side? 3. That means the cosine is, sorry, start on this side. So you go left and then right. There's 1 finger on this side, right? And 3 on this side. So for 60 degrees, there's 1 finger on the left and 3 fingers on the right. That means that your cosine and sine are root 1 over 2, root 3 over 2. Okay? So you would do sine is negative root 3 over 2. So the answer is A.
Mr. Schwartz, this is the answers D on multiple choice answers.
I think it's because when I corrected this, I changed this to a cosine. Maybe the typo was that this should have been a sine. With my current problem, the correct answer is A. Yeah, go and put A, because we changed this to a cosine. If you change this to a sine, I think the correct answer is D. So I wasn't sure which typo they made, if they actually made that a sine or if they actually made that a cosine. But yes.
It's like hand rule,
Yeah,
but I always deal with two.
it works every time. Yeah.